Welcome to the deep dive. We're sorting through some really interesting materials you sent over, textbook bits, science articles, all focused on mass, weight, and density.
Yeah, some fundamental concepts here.
Right. And our goal, our mission for this deep dive, is to really get clear on the difference between mass and weight, because they get mixed up all the time, and then understand density, what it is, how we measure it.
Absolutely. It's kind of surprising how often weight is used when people really mean mass. You hear it constantly.
Like I weigh 70 kilos.
Exactly. Kilograms are a unit of mass, not weight.
Yeah.
So, yeah, let's definitely start by pulling those two apart.
Okay, let's do it. Mass first. The sources define it pretty clearly. It's the quantity of matter in something, like the actual amount of stuff.
Mm-hmm. The fundamental amount of substance.
And then a really key point they make is that this amount, this mass, it doesn't change no matter where the object is. Earth, moon, deep space. Same mass.
That's crucial. It's constant, regardless of gravity or, even its size or shape sometimes. It's an intrinsic property.
Got it. So that's mass. Now, weight. That's different.
Very different. Weight is a force. Specifically, it's the force of gravity pulling that mass towards the center of, say, the Earth.
So Earth's gravity is always pulling things down.
Right. And that pull, that force, that's the weight. It always acts downwards, vertically.
Okay, so mass and weight are definitely not the same thing. One of the sources had a great table laying out the differences.
Yeah, that was useful. It highlighted key distinctions. Mass is the matter. Weight is the gravitational force.
Mass can't be zero, right? Because everything has some matter.
Correct. But weight can be zero if there's no gravity, like an astronaut far from any planet.
And mass is just a number, a scalar quantity.
Mm-hmm.
But weight has direction downwards, so it's a vector.
Exactly. And how we measure them reflects that difference. Mass with the beam balance, comparing known masses.
And weight with a spring balance, measuring the force.
Right. And the units. Kilograms for mass, newtons for weight in the SI system.
And the big one, mass is constant. Weight varies depending on gravity.
That moon example they gave is perfect for illustrating that. Your mass stays the same on the moon.
Because you're still made of the same amount of stuff.
But your weight is only about 1/6 of your Earth weight, because the moon's gravity is weaker.
Same. You less pull, less weight. Makes sense. It really shows weight is about the interaction between mass and gravity.
Precisely. Your mass determines how much stuff there is to be pulled, and gravity determines how strongly it gets pulled. That result is weight.
Okay, cool. Let's talk units for mass a bit more. The main one is a kilogram, kg. That's the SI unit.
And the older CGS system uses the gram, D.
One source had a neat definition for a kilogram. The mass of 1 liter of pure water at 4 degrees Celsius.
Yeah, that's the historical basis, although the formal definition is now based on fundamental constants, but gives you a good feel for it.
Then we have smaller units like grams and milligrams. A gram is 1,000th of a kilogram, a milligram a millionth.
And bigger ones too, for heavier things. The quintal, 100 kilograms, and the metric ton, 1,000 kilograms.
It's amazing how we need units spanning such huge scales. For metric tons, for trucks.
Down to the atomic mass unit, the U, for things like protons and electrons. That's incredibly tiny, like $1.66 times 1027 kilograms.
Wow. And of course, in daily life, we often measure liquids like milk or petrol by volume in liters, even though mass is the fundamental quantity.
It's just more convenient sometimes, yeah.
So how do we actually measure mass? Using balances, right? Comparing the unknown object to known standard masses.
That's the principle. And yeah, people often call those standard masses weights, colloquially, which can be confusing, but technically they are standard masses.
We got different types mentioned. Beam balance, physical balance, platform balance, digital ones.
The beam balance is the classic example. Simple lever principle.
Right. It's got the beam, the pivot, 2 pans hanging at equal distances.
And a pointer. When the masses on both pans are equal, the beam balances horizontally and the pointer is vertical. Equal masses, equal distances, perfect balance.
And for it to be accurate, the arms have to be exactly equal length, the pan's the same mass, and it should balance perfectly when empty.
Using it is pretty direct. Put your object on one side.
Add standard masses to the other until it balances. Then just add up the standard masses you used.
That gives you the mass of the object. Simple, elegant. You still see basic versions like a grocer's balance sometime.
Okay, now units for weight. It's a force, so the SI unit is the Newton, N.
Correct. And the CGS unit is the dyne. 1 Newton is $100,000 Zines, actually, 105.5.
Ah, right, $105.5. And we also see kgf and gf sometimes, kilogram force and gram force.
Yeah, those are basically the weight of a 1 kilogram mass or a 1 gram mass under Earth's standard gravity. So 1 kilogram is about 9.8 newtons.
Often rounded to 10N for quick calculation.
Exactly. And 1 GF is about 980 dynes, sometimes approximated as 1,000.
And how do we measure weight? Not with a beam balance, but a spring balance.
Right. That uses the stretch of a spring. You've got the spring inside a case, a pointer, a scale, and a hook.
And the idea is the more the spring stretches, the greater the force pulling on it.
Precisely. The extension is directly proportional to the applied force, which is the weight of the object hanging on the hook.
So you hang the object, the spring stretches, the pointer moves along the scale.
And you read the weight directly off the scale, which is calibrated in newtons or maybe kgf or GAG. Okay, make sure it reads 0 first, of course.
Got it. Simple principle again. Now, you mentioned weight depends on gravity, and gravity isn't perfectly uniform everywhere on Earth.
That's right. Gravity is a tad stronger at the poles and slightly weaker at the equator due to the Earth's shape and rotation.
So you technically weigh a tiny bit more at the North Pole than near the equator.
Yep. Even though your mass hasn't changed at all, weight also decreases with altitude.
Because you're further from the Earth's center.
Exactly. And interestingly, it also decreases if you go down into the Earth towards the center.
Why is that?
Because more of the Earth's mass is then above you, pulling you upwards, counteracting the pull from below. Right at the center, the pull is equal in all directions, so weight would be 0.
Wow. Okay. But mass stays constant through all that.
Always. Mass is fundamental. Weight is situational.
The examples in the sources helped clarify the units, like converting milligram to kilogram or tons to quintals.
And relating mass to weight. That 5 kilogram mass having a weight of 5 kilogram, which is roughly 49 newtons, 5 times 9.8.
Yeah. And those little check-in questions were good too. SI unit of mass. Kilogram. 1 kilogram. Weight of a 1 kilogram mass.
And thinking about the right units kilogram for a person, a move for an electron, tons for a truck.
Plus the conversions. 2 kilograms is 2,000 grams. 3 kilograms weigh 3 kilograms. And 2,500 milliliters of water at 4 degrees C has a mass of 2.5 kilograms because 1 liter is 1 kilogram.
It helps lock it in.
Okay, I think we've thoroughly distinguished mass and weight. Ready to tackle density.
Let's do it. Density is another key property. The sources introduce it by talking about floating and sinking.
Right, which is something we see all the time. Why does wood float and rock sink?
It comes down to density. An object floats if it's less dense than the liquid it's in, sinks if it's more dense. It's about how tightly packed the stuff the mass is within a given space or volume.
So the definition is mass per unit volume.
Exactly. Density, often symbolized by the Greek letter rho, equals mass m divided by volume v. 1 equals mv day.
More mass crammed into the same volume means higher density.
You got it. Like lead versus feathers in the same size box.
Okay. And density has its own units.
It does. The SI unit is kilograms per cubic meter, kilimi 32 eras.
And the CGS unit?
Grams per cubic centimeter, GCM 32R3.
And there's a conversion factor between them.
Yeah, $1 GCM 33 is equal to $1,000 GCM 3 weight by. That's a handy one to remember.
Because water's density is often used as a benchmark, right?
Right. At 4 degrees C, water's density is $1 GCM 33 or $1,000 GCM 3 Rs.
And iron was given as an example. $7 8 GCM 3 much denser than water.
Which is why it sinks, yeah. 7,800 kilograms 33 in SI units.
How do you find the density of something irregular, like a lump of rock? You can't just measure its sides.
Good question. The sources mention the displacement method for solids heavier than water.
Ah, Archimedes.
Kind of, yeah. First, you measure its mass using a balance. Then you use a measuring cylinder with some water in it.
And note the water level.
Right, that's V to $1. Then you carefully lower the object into the water until it's fully submerged.
And the water level rises.
To a new level, V $2.2s. The difference, V2L01, is the volume of the object.
Clever. So then you just divide the mass you measured by that volume difference.
Exactly. Density V or M, V2V1.
The examples walk through calculations like this, finding iron's density given mass and volume.
Calculating silver's density and converting it to SI units.
Finding the volume if you know the density and mass.
Or finding the mass if you know density and volume. Standard formula manipulation.
Example 5, with the spirit was good, had to convert liters to 7 meter 383 and kilograms to G first.
Always watch your units.
Yeah.
And example 6, with the glass block, you had to calculate the volume first from its dimensions, length x width x height.
Yeah, 30 by 25 by 2 gave $1,500 tonnally $33. Then divide the mass, 7.5 kilograms or 7,500 grams by that volume.
It shows how you apply the basic definition in slightly different scenarios.
And those fill-in-the-blanks helped recap density alongside mass and weight concepts. Weight depends on gravity and mass. Mass is never zero. Beam balance arms must be equal. 1 kilogram linked to 1 liter of water at a 4 degrees C.
Ties it all together.
Okay, one last concept from the sources. Relative density. Why do we need this if we already have density?
Well, sometimes just saying something is heavy or light isn't precise enough, especially if you're comparing equal volumes. Relative density gives a standard comparison point.
Comparing everything to water.
Exactly. Relative density, sometimes called specific gravity, is the ratio of a substance's density to the density of water at 4 degrees C.
So frac density of substance density of water.
Or, since density is mass volume, it's also the ratio of the mass of a certain volume of the substance to the mass of the same volume of water at 4 degrees C.
Okay. And because it's a ratio?
It has no units. The units cancel out. It's just a number.
Which makes it easy to see if something is denser or less dense than water. If RD is greater than 1, it's denser. Less than 1, it's less dense.
Precisely. The table showed things like alcohol 0.82 and petrol 0.72 being less dense than water, RD they float.
And mercury 13.6 is way denser.
Even air has a relative density, just very small, about 0.00013.
How do you measure it for liquids?
The sources describe using a specific gravity bottle, or RD bottle. It's designed to hold a very precise volume.
Okay.
You weigh the bottle empty, M$1, then full of water, M22, then full of your liquid, M32.
So the mass of the water is 2 M$1.
Yep, and the mass of the same volume of the liquid is 3 M$1.
So the relative density is just the ratio of those masses, M31, M2, M1.
That's it, a practical way to compare liquid densities accurately.
Okay, wow. So wrapping this deep dive up, we've definitely untangled mass, the amount of stuff, always constant from weight, the force of gravity, which changes. We looked at their units, how to measure them.
Then we explored density, how much mass is packed into a volume, and saw how to calculate that using methods like water displacement.
And finally, relative density, which gives us that unitless comparison to water, telling us quickly if something will sink or float.
It covers the fundamentals really well.
So here's something to leave you thinking about. We talked about density determining if, say, a log floats. But the sources hinted at larger scales, like convection currents. Consider how these slight differences in density may be driven by temperature or salinity in water or temperature in air, actually drive huge systems on Earth, like ocean currents influencing global climate, or atmospheric circulation creating our weather. We see density in a glass of water, but maybe pause to think. What other vast, complex phenomena around us are ultimately governed by these simple, fundamental principles of mass, weight, and density?
It really makes you appreciate how interconnected physics is with the world around us, from the smallest particles to the largest systems. A lot to ponder there.